And at this point, we're going to start taking a look at the motions of fluids at a very fundamental level. So we already talked about velocity fields. Now, the velocity field is a vector field. It has three components: u, v, and w. In this class, this is how we'll be describing velocities. U is the velocity in the x direction, v is the velocity in the y direction, and w is the velocity in the z direction. And we have our I, j, and k direction unit vectors. So there's three components to the velocity, but the velocity also depends on the x, y, z, and time coordinates. So the velocity is going to tell us how quickly the fluid is moving and the direction it's moving in. Now, this flow can be considered 3D, 2D, or 1D, and this depends on the number of dimensions required to determine the velocity field, not the number of components to the vector. So most real flows are 3D. You have to know the x, y, and z coordinate to determine the behavior of the flow. Most engineering analysis requires at least 2D analysis to get the complete picture. We can usually ignore one coordinate direction and still get a pretty good picture of the overall behavior of the flow. For many engineering problems, we want to simplify the system and come up with something that we can quickly come up with a solution. And so in that case, 1D analysis is sufficient. So CFD codes like star CCM or CFX or Fluent look at 3D behaviors. Codes like relap or trace or gothic tend to use 1D analysis to very quickly solve very large systems. If we look at the picture on this slide, we can see that in this entrance region, the flow is two-dimensional. It depends on the radial coordinate and the z direction coordinate. So it depends in this case on z and r. However, when we get further down the pipe, we have a fully developed velocity profile, which no longer changes with z. So in this case, it only depends on r, and it's 1D. So even though the velocity is there's only one component throughout here. There's only an r component to the velocity. Or I'm sorry, there's only a z component to the velocity. It's 2D here because it depends on r and z, and it's 1D here because it only depends on r. Now, so streamlines are lines that are tangent to the velocity field. They're always tangent to the velocity field. That means they're parallel to the velocity vectors, and they're always parallel to the velocity vectors, so there can never be any flow across a streamline. What a streamline does is it traces where the flow is going at a particular time. And we can actually determine the definition of a streamline just from its definition. So we can look, dy dx for a streamline is going to be the y velocity over the u velocity. And we can also get dz dx and dz dy. So we can come up with this equation where we have dx over u equals dy over v equals dz over w. And we can use this to solve for streamlines. And we'll do some examples of that in class. We can actually visualize streamlines using particle image velocimetry. So we take two pictures a very short time apart, and we use a computer algorithm to determine where the points from the first picture have moved in the second picture. And we can put velocity vectors on those points. We can also look at stream tubes. So streamlines are good for 2D flows. However, in 3D flows, we have these ideas of stream tubes. A stream tube is all the streamlines around a closed curve. So we can take a look. Here's our PIV. And here's our stream tube. So each of these is a streamline, and we have this circle of streamlines, and then it moves, and now we have this same curve made by all the same streamlines we had before. Just like a streamline, since it's made of streamlines, no flow can cross this stream tube. We can also make the stream tube infinitely small, and that gives us a stream filament. Now there's no flow, so what does that mean? If there's no flow across the streamlines, or into or out of the stream tube, it means when streamlines are further apart, the flow actually is slowing down. And when streamlines get closer together, it means the flow is speeding up. So we can look at streamlines to get an idea of how the flow is behaving. In addition to streamlines, we also have path lines and streak lines. Now a path line is the line that a single particle of fluid traces as it moves. So we have dx dt and dy dt, which are determined by the u velocity and the v velocity, the x velocity and the y velocity. It's the actual path that one single particle takes. We can actually visualize this if we tag a particle with dye or smoke or a radioactive isotope, and then we measure how it moves as it goes through the fluid. We get the path line. We can actually find this by integrating the velocity field. So if we take dx dt equals u, and we integrate with time, then we get x is the integral of u with time. The streak line is a line that connects all of the fluid particles that have passed through a particular point. So basically what happens is we tag all the particles moving through a point and we watch where they go. And this is what we do when we're in a wind tunnel, for instance, when we want to see the flow over a car. We tag all these particles one after another and we look at the line that that tag makes. So to find the equation of a streak line, first we have to find the path line of the particle, and then we actually have to reinterpret the equations. We start out with the path line of the particle, and then we reinterpret the equations. We move them back around the other way, and we start with a particular time, and then we look at the position at time 0 of all the particles that have passed through that point at any time. So we'll discuss this more during class. We also can look at steady and unsteady flow. Steady flow occurs when the fluid properties at a particular point do not change with time. So the time derivative is 0. However, properties can still change with location. So you can still have a df dx or a df dy or a df dz. In steady flow, it's actually can be proven that the streamline, streak line, and path line all have the same equation. They're all identical. An unsteady flow is one where the properties do change with time, so time derivatives are not 0. And in this case, all those different streamline, streak line, and path line are different. They don't follow the same line. Now, steady flow is a useful idealization that we can use to simplify a lot of problems, and then we don't have to worry about how the flow is changing with time. We can also look at what we call a uniform flow. Now, most flows are not really uniform. However, we usually can assume that the flow is uniform for certain applications. This usually requires the assumption that the flow is inviscid because we need to violate the no-slip boundary condition. But it's often useful for control volume analysis, where we don't necessarily care about all the details of how the flow is behaving, we just care about the average. So then what we can do is we can say the velocity of the fluid everywhere is the same as the average, which gives us our uniform flow. We can also look at averaging the velocity. Now, the average velocity is just defined as integrating velocity over area, then dividing by area. So you're just summing and dividing by the total number of samples to get the average. However, it's important to note here that we have this dot product. So velocity and area here are both directional quantities. You have a unit normal vector on your area. So we need to have the sign of this dot product. If the velocity is into the control volume, then the vector and the velocity and area vectors point in opposite directions, and we have a negative dot product. And if the velocity is out of the control volume, then two vectors point in the same direction, and the dot product is positive. So we need to pay attention to those signs when we look at average velocities or flow rates and things like that. We can also define a volumetric flow, or Q, which is the rate at which the volume of a fluid flows through an area. The reason we do this is because it's often easier to measure than the real velocity of the flow. And we can relate that to the average, so we can say the average velocity is volume flow rate divided by area, or volume flow rate is velocity times area. And then last we have the mass flow rate. So the mass flow rate tells us how quickly a unit of mass is moving through an area. And again, the reason we like to use this is because it's much easier to measure than the actual velocity of the flow. Sometimes it's even easier to measure than the volumetric flow. But again, we can relate to the average velocity. So the mass flow rate is the density of the fluid times its volume flow rate. or VA. So we can relate it to average velocity as mass flow rate equals density times velocity times area.